The next question is a 6-mark question, and it's about line spectra. So this again is the second topic, energy levels and line spectra. And it's worthwhile taking a look at the mark scheme. So the key thing in this sort of question is you must make sure you're reading the question extremely carefully. So you've got a line spectrum. We know that there are two types of line spectrum, either emission or absorption. So it's going to be one of those two that I'm looking at. And which one it is? Well, it says, you should describe how the collision of charged particles with gas atoms can cause the atoms to emit photons, how the spectral lines are explained by the concept of discrete energy levels. So this is an emission spectrum that we're dealing with here. Okay, now let's take a closer look at what they say in the mark scheme, because it's important that we understand what it is that they want us to do in order to achieve top marks. So if we look at the bottom marks, 1 to 2 marks, it says discussion of one element, and we'll look at what we mean by one element in a moment, only incorporating at least 2 points. So it says at least, right? It doesn't say a maximum. Now what that means is I could put in 6 points that were correct and still only get 1 to 2 marks if the examiner decides this is the level of my answer. So let's jump up here to the top and see what is it that gets us the top marks. Some of the key things: we have to present relevant information and it has to be presented coherently. So that means they want us to give those facts in order to support an argument that we're making in a logical way. So the content of the information we're putting in has to line up, has to support what our argument is, okay? And we also have to employ a structure style to make sure that the meaning is clear, okay? This one is also important. The text is legible. Be aware that this is marked by examiners. If they have difficulty reading something, it's highly unlikely they're going to spend long periods of time trying to decipher your writing. If your writing is poor, particularly under pressure, practice writing now clearly, so that by the time you come to your test, you're able to write more clearly and quicker. One of the ways to write more clearly is, instead of writing joined up, is to write with the letters separated. Okay, it initially will take a longer time, but if you practice this, it will become faster. Okay, and what they want is they want a good discussion of both elements in question, making at least 4 points for each element. So we need to have 4 relevant things said for both elements so that we make a coherent argument. Okay, so let's take a look at what the elements are. Well, it says in the question what the elements are. The 2 elements are how the collision of the charged particles can cause the atoms to emit photons. That's the first part. And the second part is how the spectral lines we see are explained by the concepts of discrete energy levels. So, the collisions. So I'm going to go for, this is 1, this is 2. So I'm going to go for element 1 first of all. And I'm going to start by saying the collisions. Now, it is a good idea when you're doing this sort of question not to immediately jump into writing. Just try and think about the things that you're going to say initially. So we have, for element 1, we've got the transfer of energy from the free electrons or the charged particles to the orbital electrons. That causes the excitation, that is, the electrons go to higher energy levels. I'm just jotting some notes, hard to read, but it's fine so long as I can read them, because it's not my main text. That causes the excitation of the electrons to higher energy levels. They then fall back down, releasing a photon. So it falls back down and releases a photon. So there, it said 4 points. That would be 4 points for my first part. And for my second part, how the spectral lines are explained, using the idea of discrete energy levels. So the photon energy depends on the frequency. That's going to be my first point. The spectral lines at discrete wavelengths. That would be my second point, wavelengths, which also are frequencies. Therefore, the line corresponds to energy level change, so the electron going down in energy level. And we've got different ones, the different lines correspond to different energy level differences as it falls from, say, 2 to 1 or 3 to 1 and so on. Okay, so we have the collisions. We're going to start with the collisions first of all. So the collisions transfer energy from charged particles to the electrons in the atoms. This causes them to be excited to a higher energy levels. The electrons will fall back down, emitting a photon. Emitting, or in this case photons, because I've said electrons, emitting photons. So that was my first part. And then my second part is the energy of a photon depends on the frequency or wavelengths given by energy is equal to hc divided by lambda. So I've related the energy to the wavelengths. Okay. The spectral lines are at discrete wavelengths, which corresponds to photons of particular energy. So spectral lines are at discrete wavelengths, which corresponds to photons at particular energy. And then we can say that this is given by the difference in the energy levels as the electron falls down. I've already got really 4 points here, but we can finish by saying a larger transition means higher energy, hence a shorter wavelength. Okay, so the key thing is we've answered both parts of the question, and we constructed this argument going from the collisions, transferring the energy, all the way to how this means that we end up with wavelengths at discrete and different values. Okay, moving on to question 4. Very common question. What phenomena can be used to demonstrate the wave property of electrons? This is almost always, the answer is almost always diffraction. There are other things you could say here. You could say refraction, you could say interference, you could say superposition. The one that's always in the mark scheme is diffraction. So electrons can be shown to diffract. So that means that they have wave properties. Then says calculate the wavelength of electrons traveling at this speed. By the way, this is obviously the wave-particle duality part of our topic. Wave-particle duality means that the photons or the electrons, they have both wave properties and particle properties, and they're either demonstrating one or the other. Okay, so calculate the wavelength. So what are we going to do here? Let's turn to our equation sheet. I'm looking at the de Broglie wavelength equation, which tells me that the wavelength is equal to h over mv. I'm told what the speed is. It's 2.5 by 10 to the 5 meter per second. So this is going to be 6.63 by 10 to the minus 34 joule seconds divided by the mass of the electron, excuse me, multiplied by the speed, and notice I'm putting in my units. Once again, you can check that the units work out correctly. We should end up with units of meters. And that gives us an answer of 2.9 multiplied by 10 to the power of minus 9 meters. Note the number of significant figures I've put in here. I've put in 2. Now the next question says calculate the speed of the muons with the same wavelength as these electrons, and we're told that the mass of the muon is 207 times the mass of the electrons. Now we can do the same thing. We can use the same equation. We can work out the mass of the muon from the mass of the electron multiplied by 2.7. So we could end up with an equation that says the wavelength is equal to 6.63 by 10 to the minus 34 divided by 9.11 by 10 to the minus 31 times 207 times the speed we want, and that would be equal to 2.9 by 10 to the minus 9 meters. And we can work out our kilograms. We can work out what the V is. We could do that. But you should see that whenever we, because this wavelength has to be the same, if we increase the mass part, in this case by a factor of 207, clearly the speed has to go down by that factor. So the speed, so very simply, the speed is going to be 2.5 by 10 to the 5 divided by 207. So in many ways that question, and it is perfectly fine to do it by writing out the equation and putting the numbers in. It means you'll always be sure of getting the right answer. But we can note that this is a very simple question in reality. And very quick to work out. Just per second, and this had no units. Okay, in terms of writing the answer here, we had 2 significant figures here. We've got 3 significant figures here, which means we should write it to 2 significant figures, which give us an answer of 1200. Right, question 5, the photoelectric effect. This can be demonstrated by illuminating the negatively charged plates. Ultraviolet light shows it loses its charge. Explain why when it's shown on a positively charged plate, no charge is lost by the plate. Now, I want you, when you think about this question, I want you to go back and look at the work you did researching the gold leaf electroscope and its use in the photoelectric effect. And if you remember, it looked like something like this, where we had a device that looked like this with a piece of gold foil. And what happened was we charged it so that the gold foil moves away from the central column because they've got like charges, so they repel. But once we shine light onto this, what happens is the electrons start to leave the electrons are emitted. So we have the UV light comes onto the piece of metal. The electrons are emitted, which means we have a reduction in the charge, which means the gold foil comes down. We lose charge. Okay, now the second thing I'd get you, so just go back and make sure you've fully understood this experiment. And I'll also draw your attention to the fact that the question asks, explain why when the UV is thrown on a positively charged plate, no charge is lost. Whereas when it's said here, when it's a negatively charged plate, charge is lost. Note the use of the word charge. They're talking about the photoelectric effect, but instead of talking about electrons being lost from the metal, they're talking about charge being lost from the electron. Okay, so let's take a look at what we're talking about here. So here I've got my gold leaf electroscope, but this time I've charged it, so now it has an overall positive charge on the device like this. This does not mean that there are no electrons. There are still free electrons in this piece of metal. It's got charge. It could be a very small charge, let's say +2 elementary charges. That's positively charged. It just means I've removed 2 of the electrons, so I've got 2 more ions in the total number of ions in the metal compared to the number of electrons. Okay. Now, in this case, when I shine my UV light onto the metal plate, remember, this will have enough energy to overcome the work function, so an electron has to be emitted. An electron that's at the surface would be emitted with maximum kinetic energy so long as the energy of the photon is above the work function, and we know that it is because that's what they said at the start. So even though this thing is positively charged, it will still cause the emission of an electron because that's what the photoelectric effect does. However, what will not happen is this will not come down. Why not? Because the overall positive charge has now increased rather than decreased. Okay, so the photoelectric effect will happen, which means electrons are emitted from the surface of the plate. However, as electrons are negatively charged, this will increase, not decrease, the overall charge on the plate because it's positive. Okay, so this question is a subtle question. It requires that you have complete understanding of this experiment with the gold leaf electroscope. Right, next part, it says we've got the threshold frequency and the work function are shown for the work function for 3 different materials and the threshold frequency for 3 different light. Now this is unusual, we've got a 6-mark question, we don't have a lot of space here. So once again, it's really important to think carefully about what you're going to answer in this case. So let's look again at what is it that gets us the mark. Once again, they're saying relevant information presented coherently. They've said here there should be 2 ideas fully analysed with a full discussion of alternatives. So what are the 2 ideas here? The 2 ideas are we need to demonstrate the work function, the idea of the work function, and we need to demonstrate the threshold frequency. This is to do with the material, because it's the work function. This is to do with the light source. Okay, so what we are saying is what we should be able to do, we want to demonstrate the effect of threshold frequency on the photoelectric effect. So we need to vary the light frequency and observe the effect on the photoelectric effect. Let's call it impact, just so we don't end up with too many effects. So we vary the light frequency to observe the impact on the photoelectric effect. This one, we're going to vary the material, and we're going to again observe the impact on the photoelectric effect. So essentially what we're being asked to do is say, to be able to demonstrate this one, we need to use at least two materials. So we're going to pick two of the materials and see that with one of the materials we don't get the photoelectric effect, with a different material we do get the photoelectric effect. So I'm just going to put this in bullet points. For the photoelectric effect, we could have the options of, if I was to take zinc, which is 4.3 electron volt work function, and let's say iron, which is 4.5 electron volts. Okay, with one of these I want to see the photoelectric effect, with the other one I don't. So this one's got a higher work function, so I want to not see, I don't want to see the photoelectric effect with this one, I do want to see it with this one. So if we look at the light sources, if I do it with light source 2, it has an energy of 4.4 electron volts. That means we will see the photoelectric effect with the zinc, we will not see it with the iron. So that would be one of my options. An alternative would be to have the zinc and the copper with light 2, or we could have, well no, that would be it, because if we look at the light sources, with one will never have enough energy for any of the materials, whereas light source 3 at 5 electron volts will always work with any of the materials. So it has to be light source 2 with zinc and iron, and we could mention that none of the other light sources will work. No other light source will work for this. Okay, although we could use copper, I think. Then we have the frequency demonstration. Here we're varying the light frequency, so we're going to pick a single material, so we could have the zinc at 4.3 electron volt work function. So light source 1, that's 4.0 electron volts, so no photoelectric effect here. And light source 2 at 4.4 electron volts, that will work. So we'll see the photoelectric effect here, not see it here. We could also do it with light source 1 and 3. And we could use iron with light sources 2 and 3. So this question was all about making this decision first and then writing the answer and showing that you've got a combination of light sources and metals for these two parts to the answer. Then we have part C, which says calculate the maximum kinetic energy emitted from a zinc plate when illuminated with ultraviolet light. We're given the work function and we're given the frequency. So we're going to use the equation HF is equal to the work function plus the maximum kinetic energy. So that gives you maximum kinetic energy is equal to HF minus the work function. Now that means I need to have the work function in joules, so it's going to be 4.3 electron volts multiplied by 1.6 by 10 to the minus 19 joules per electron volt to give me an answer of 6.88 by 10 to the minus 19 joules. I can now substitute that into my equation, so I'm going to have EK max is equal to 6.63 by 10 to the minus 34 joule seconds, multiplied by F frequency, which is 1.2 by 10 to the 15 hertz, minus 6.88 by 10 to the minus 19 joules. That gives me, I'll just turn up the page so it's in here, that gives me 7.956 minus 6.880 times 10 to the minus 19 joules. And that gives me an answer of 1.076 by 10 to the minus 19 joules. So my answer, and here in the question, I've been given two significant figures, so I'm going to write the answer as 1.1 multiplied by 10 to the minus 19 joules. Now, why is this answer a maximum? This answer is a maximum because the maximum kinetic energy corresponds to when electrons are already at the surface. Electrons that are deeper in the metal will be emitted with lower kinetic energy.